Part 2. How do we charge objects? The most common way that you are aware of is rubbing two objects together. When two different materials are rubbed together, one of them may have more affinity for the negatives, and one object's loss is another's gain. Affinity means attraction. When electrons or negative charges have moved from one object to another, which object is now positive and which is negative? So if we look, you need to count the total or net charge on each object to determine its total charge. Black and red are original charges. Light gray indicates an electron that left a spot. Dark gray indicates a new electron at the location. The blue arrow shows the electron moving from one object to another. So it's common in electricity to talk about either charge moving, but in reality only the electrons can move. But we can equally say positives move. The end result is the same. We can say the negative charges moved from this object to here. So if we look at the original total, there was an equal number of positive and negatives on both. Cancel, 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 cancel. But two of the negatives went this way. So this object is now net negative. This object is now net positive. When does this happen? Well, again, human beings with no social life at all created this table in your textbook. So there was some point in time where someone grabbed a rabbit and rubbed it on a cat to see which would happen, like in terms of electricity. Probably a whole lot more happened, and there's probably the guy that died attempting to rub a tiger on a bear. But this is the Electrostatic Series, created before there was an internet and social life in the evening. So Benjamin Franklin and other people sat around there just rubbing things together and seeing what would stick to the wall. Now, let's say we rub a rabbit fur onto cotton. What they discovered was the rabbit fur doesn't really gain electrons easily, so it loses its grip on some of its electrons, and the cotton grabs a hold of electrons better, and it pulls them to itself. So whoever is lower down on this chart is greedier for electrons. So if you rub polyester on rabbit fur, you will find the rabbit becomes positive and the polyester becomes negative. Now, cat on a wool rug is a lot of fun because I used to drag my cat around the house on the rug, and you charge them up and then they get really mad at you because they eventually learn they're going to get shocked. So you can try this at home, rubbing a cat on the carpet. It's something that entertained me quite a bit when I was younger. So you have to do a basic read on this chart for me. You have to be able to tell me what's going to be the result of wood being rubbed on glass. Okay? Because these kind of situations occur in real life all the time. So it's a highly practical skill to be able to know what happens if you rub a kangaroo and a crocodile beyond the ecological properties here of predator-prey relationships. You want to just find out, this kangaroo was all like staticky before the crocodile ate it. Now, this is what I'm talking about, cats and static electricity. They're not really keen on the idea. So when you yank the sweater off the cat before it claws your face, you're going to get charged. So when the cat gets the cotton sweater yanked off of it, the cat's fur will lose electrons to the cotton. Now, the big question is, after this affront to the cat's dignity, will it go pee on your bed or your sofa because of you putting it in the sweater, which from the cat's expression, it's like you're going to pay. Now, this leads an object to be in an unstable situation. They don't want to be charged. They want to be neutral. So after you walk across a rug and you pick up, say, extra electrons on your body, they will attempt to leave the minute you touch a conductor and you get shocked. So if they are separated by an insulator like air, they may retain their charge. So the strings on the Van de Graaff stand on end until such time as we ground it. So when you touch them together, they will neutralize because the charge excess can now redistribute itself to a nice new level. So touching them to a grounded conductor is one way, or touching them to an opposite. And so we generally refer to that as grounding. So what happened at home when I was a kid, cats do nose greeting. Well, the cat you rubbed on the carpet would eventually go sniff the nose of the other cat, and you'd hear like the snap, and I'd just giggle. Please don't call the authorities on me. This was like 40 years ago. I don't do rubbing cats on carpets anymore. It's like I've gone beyond that. Now, where do these XX electrons go? Well, weren't created when you rubbed your feet on the carpet. Let's suppose you stole electrons from planet Earth. Well, when you feel the shock of them leaving, the Earth got its electrons back. And even locally, if a lightning bolt hits down and dumps a massive quantity of electrons, say in Kansas, well, all the wheat in Kansas isn't going to stand on end. The Earth will allow those electrons to spread out. Because remember, they hate each other. So even through rock, there's enough voltage behind a lightning bolt. Those electrons leave the area. Though, if you're in an area near a lightning storm and your hair begins to stand on end, it means charges are accumulating around you. Get out of there. Now, it would be kind of interesting if we could rub the Earth on a giant sweater and stick it to the moon, but I think you just get your sweater wet and smeary with oil spills and everything else like that. Now, in England, the country that gave us hoovering for vacuuming, they call electrical grounding earthing. You know, did you earth the conductor? The second method is charging by contact. So I want you to make object B neutral and A net negative. Demonstrate how charging of B would occur. What would happen when you touch the two together if A had more negative charges than it should have? So it's mostly negative. Would they both wind up being negative? One negative, one positive? Would the resulting charge be stronger or weaker than the original? And this is something we'll take up in class. Now, what about grounding an object? Connecting a charged object to ground, literally the planet Earth, or a sufficiently large object will allow the charge balance to neutralize. So the Van de Graaff is just a thin little aluminum foil ball. So when I touch it, even if I'm wearing insulated shoes, I'm grounding the thing because my body has a lot of meat to spread out those charges. So electrons can leave through the ground or they can come back in through the ground. So the big thing about the Van de Graaff is since it's positive, when you reach to touch it and function as the ground, you hit the Van de Graaff with your sparks. They're leaving your body. That's why they sting so much, because they're coming from one single spot. So you're actually grounding the Van de Graaff by throwing the electrons back onto it. So I want you to try to draw the neutralization of a small charged object being neutralized by touching it to a huge object, or neutralize it by ground. How would you draw the charges on this to demonstrate these two situations? Now, the third method is called induction. And this is the hardest one for people to explain. So I'm going to pause the slideshow here again so I get a chance to do induction in a single pass so you get a better idea of how this works. This method is used frequently in our technology today. It's why balloons stick to walls, and it has vast implications for how lightning strikes behave and what you should be watching for in terms of signs. So while it's new, it's actually one of the most important methods, and its understanding will give you a great appreciation for lightning and the technology that uses static electricity.